Yes, good evening. My name is Donald Adams. I am presenting my Spectral organ. I dedicated this project to my mother, Elia Adams. I'm an E&MU student majoring in electronics engineering technology with a specialization in renewable energy. The goal of my project is a noise meter. I want to detect the level of noise using an auxiliary cable at 512 hertz using filter. There are different spectrometers already on the market. On the Apple App Store, for example, you can tune your musical instrument to a corresponding note. So if you wanted to tune your musical instrument like a guitar, you would be able to do that, mapping out each frequency to a specific color as well. Here's a color organ kit that you can order from Jameco. The kit is $25. I assembled it myself, and it was relatively quick and easy to build. Only took me 2.5 hours to make. And here's a demonstration. So there's another DIY kit that you can look at on Instructables that's very similar. And here for the low frequencies, there's higher values of capacitance and resistance. For the high frequencies, there's low capacitance and lower resistance. This is because the frequency is 1/2 pi RC as the time constant, and that's supposed to filter out low, medium, and high frequencies, and it doesn't. And here's what happens.
Low frequency, high frequency response.
When I put the low frequency, all the lights will light up.
High frequency response.
When I put the high frequency, all the lights will light up even faster. Here's another DIY kit with a microphone.
The frequency response to the tuning fork.
And I had a tuning fork that I ordered on Amazon for $6. It's 512 hertz, which is part of the reason why I designed this filter, to filter out that specific frequency. When I came across the third order Chebyshev, I ran into some complications, and it's very complicated to build for low frequencies. Here is the mapping of specific musical frequencies corresponding to those notes on the piano. As you can tell, the violin covers a higher range of frequency, ranging from 196 hertz all the way up to 3.1 kilohertz. You can tell that this also includes the harmonics. So C1 is 1 times 33 hertz. If you multiply that by 2, you end up with 66 hertz. Multiplied by 3, you end up with 131 hertz, so on and so forth. As you can see, there's 7 octaves on this piano, and a difference of about 8 hertz between one musical note and the next one. This one would be A, this one would be B, this one would be C, D, E, F, and G. So the guitar actually has a relatively mid-range of frequencies, and your voice actually doesn't cover as high pitch as the guitar
Hello,
does.
Classmates. I was able to implement both the TL074 low-pass filter and high-pass filter using the same IC.
So I implemented the TL074 integrated circuit. This is optimal for the lower frequencies. I implemented both the low pass and the high pass filter using the same IC.
TL074 IC has a very high slew rate and can be implemented using low voltage.
So it has a low voltage and high accuracy of dropping the skirt off for differences of 8 hertz between each different musical note. Here we're centering the frequency around 128 hertz.
So they're both centered around 128 hertz. This is the low and high pass filter, both on the same IC. We have the same thing with the soldered version of the high pass and low pass.
Here I soldered the printed circuit board version of it, and it have
around
the
128
same
hertz. If we lower the
response to the
frequency, the
low pass
and if we
frequency would have
increase the
passed the
frequency,
low
then the high
frequencies, and
pass
the high
filter
pass
activates.
would pass the high frequencies. If you would like to build this circuit yourself, here is the bill of materials. If instead of a TL074 you only have the 358, that works too. You need the 3904, however, because that is going to be your BJT that will connect directly to the LEDs. Here's the electric microphone that you can purchase online for $6. The resistors and capacitors depend on the frequency that you designed your filter to match. Then you would need a breadboard or a soldering board, depending on your specific design requirements. Then for testing purposes, you'll need a oscilloscope, power source, and wave function generator.
This is the bandpass filter, centered around 128 hertz. Low frequency doesn't pass, neither does high frequency.
So here you can see whenever the wave function generator is inputting a low frequency, it will not allow signal to pass through it. Neither will the high frequencies go through the filter. Using Capture CIS, which was formerly known as AutoCAD or PSpice simulation, you can simulate with the specific components. This is the design for the filter using 1 nanofarad capacitor, 10 kilo ohm resistor, 10 mega ohm resistor, 2 mega ohm resistor, and this is for the 512 desired cutoff here. So the tuning fork was 112 hertz, and here, as you can see on the logarithmic scale, there is a very sharp skirt cutoff there. I put a 2-stage amplifier on a printed circuit board, and this is what happened.
This is the circuit with the second stage amplifier.
So I can pick up the sound signal from this microphone and amplify it through the two BJT common emitter amplifiers.
This is the battery version of the same circuit. Here you can tell that it's still working without the power.
So I connected a battery source to this using a voltage regulator. However, whenever I tried soldering it, things got hairy and it stopped working. So I continued after this portion of the project using the DC power supply. So going back to the microphone circuit, I implemented 2 of these common emitter amplifiers that are cascaded with each other to multiply each individual amplification of negative 90 volts per volt. Here is the same thing, this time using OrCAD Capture PSpice. As you could tell at this time, there was an error with the netlist. And since I resolved that issue, there were 2 capacitors here that it did not like. Once I got rid of one of these capacitors, it gave me a very beautiful sine wave output. And as you could tell, the input was so tiny in the millivolts range, it was negligible compared to the output, because 90 times 90 is about 840 volts per volt amplification. Here is the same circuit using the printed circuit board. These are 3904 transistors. The printed circuit board version of the filter is right here. You could tell with the BJT there is an emitter follower, and that acts as a buffer. Then there's an LED attached here to the 2 female headers. This third female header has the TL074 integrated circuit. Then we're using 1 operational amplifier to amplify the input further here at the input, and then filtered through those 2 capacitors and 2 resistors at the output. Thank you very much.